speaker, Mathilde, who is going to talk to us about, let's see, generating, all right, let me find your talk here. Generating the pelagic size structure database, which I think we're all quite interested in. So without further ado, Mathilde, I'll hand it over to you.
Thank you. Okay, I will share my screen. I hope you can hear me well. All right. So I'm going to be presenting PSSdb, which is a global pelagic size structure database that we are building from multiple imaging devices. And when I say we, it's really me presenting on behalf of a team of researchers from NOAA, who are based in the US, and a researcher based at the laboratory of oceanography of Villefranche in France. So the team includes myself, Marco Corrales. We are the postdocs working on ingesting data into PSSdb, and then the co-lead PI are Jessica Luo and Rainer Kiko. So why are we interested in building a pelagic size structure database is because size is often seen as a master trait for many disciplines of biological, physical, or chemical oceanography, but it also has a lot of impacts, environmental and societal impacts. Some of them include carbon fixation, which we've heard of, but mainly from photoautotroph, which is represented here by the circle. You see that it scales up, it usually scales up the amount of carbon per cell produced by photoautotroph, usually scales to the size, but it's also the same for respiration and production of oxygen by the same autotroph, but also heterotroph, as well as nutrient uptake also usually scales to size. So this all, of course, has an impact to the global CO2 uptake and oxygen production and consumption, and like all the OMZ, etc. Then for physical oceanography, what we tend to use as a model is the rate of, to predict the rate of sinking is using the Stokes law. So this relates the size of the particle to sinking speed. And we can see that it scales for various marine organisms. And this has an impact on carbon export and sequestration. And finally, for ecology, we know that usually a size ratio between a given predator and its prey is usually predicted to be a 10th, and that's due to this very well correlated relationship between the predator, the size of a predator and the size of its given prey. So this also has impact on the amount of carbon transferred to higher trophic level into commercial stocks. So how did we decide to study and to build a pelagic size structure database is using a few imaging sensors. Here you have this publication by Fabien Lambert and colleagues in 2019 that shows that we have now a range of imaging device that allows us to capture the size of the broad size spectrum of pelagic organisms, from the small phytoplankton using the IFCB or imaging flow cytobot to larger organisms with the underwater vision profiler, as well as the in situ ichthyoplankton system. So that's the ISIS. So we've decided to build a workflow in order to consolidate, harmonize, and process all the images that are being collected by the IFCB, the UVP, and the ISIS, and the ZOOSCAN as well, to predict global pelagic size structure database. So the code will be posted here, For now, the access is restricted, but it will be publicly available upon the first data release, which is supposed to be early next year. So like I said, we are going to be using multiple imaging device, and each one of them has a specific target for the organisms that they detect. We are going to be using the imaging flow cytobot that typically image organisms from 5 to 100 micron size, and it includes both autotroph and heterotroph. And then the underwater vision profiler and the JETZON will be used to detect organisms from 100 micron above to a few centimeters length. And the in situ ichthyoplankton system will be used for fish larvae or even fish or jellyfish, so for the largest organisms. Now, each of these instruments is typically used with a specific mode of acquisition, which of course provides a lot of information, but it also represents quite a challenge to try to consolidate data from all those instruments together. So, for instance, the IFCB is typically used underway, so we only get images from the surface layer, whereas the undervision profiler and the JETZON are typically used as profiler or as a way to image vertical nets. So it really gives us an idea of the depth profile of different organisms, and the same for the ISIS, which is a towing instrument. So the depth resolution is different across those instruments, so is the temporal resolution and the source of all those data. But despite those challenges, we actually managed to produce what we're interested in, which is the NBSS, or normalized biomass size spectrum. So I'm going to walk you through the workflow. The first step consists in just using different the API of the data source to try to list project all in an automated fashion. And so for that, we just ask person who want to collaborate with us and have data hosted on Ecotaxa or on their dashboard to give us access. So we've generated sort of a generic account that each of the member of PSSdb can then get access to the data and export it. So that's step 1, and step 2 is just getting the data. Step 3 is just performing quality check and checking that there's no missing or incorrect metadata or data, that the detection rate was coherent, etc. And then the next step is then to standardize and harmonize, because each of the data files that we are getting for those instruments are really not constrained in any way, so that it's easy for people to just upload their data and annotate the images without having to standardize the name and the units, etc. So this is a work that we are doing. So we are making sure that the data file, all the data files that we are getting, regardless of their native format, that are then formatted into with the same variable, the same name, the same unit, and that correspond to standard vocabulary. And then once we have the standards file, the goal is really to grid that into spatial bin, but also size bin, and to calculate NBSS. So what is NBSS? It's just the sum of the biovolume divided by the sample volume divided by the size bin. And so we get this value for each size bin. And those projects will be then posted on the NOAA PSSdb database. So this is what the spatial scale of the project we have ingested so far in PSSdb. We've right now only have data coming from the imaging flow cytobot, the underwater vision profiler, and the ZooScan. But you can see that the UVP and the ZooScan already cover a pretty broad range. And the goal is really to maximize that range. The IFCB, on the other hand, is really only limited to polar regions. And this is what their NBSS would look like. So the first thing to notice is that typically for NBSS, what we observe is a decrease of the abundance of organisms with increased size. So the x-axis represents the size estimated from the area, so that it's produced as equivalent circular diameter, and the y-axis is just the sum by a volume divided by the volume sample divided by the bin width. So it's roughly equivalent to a number of individual or particles per liter. And so you see the number of particles per liter typically decrease for all the instrument. The other thing you'll notice is the different scale between the instrument. Of course, the IFCB is able to detect smaller organisms, so that their abundance is typically higher, up to 1,000 organisms per milliliter, whereas the UVP and the ZooScan have mostly up to 1 or 10 organisms per liter, because they typically detect organisms that are about 1 millimeter and above. Here you'll notice some shift in the size spectrum. Is just due to different mesh net type which have different mesh. So that allows us to see roughly organisms that are around 300 micron or less. I've color-coded all the NBSS by latitudinal range, but I don't think we can see really a pattern here. So the ID, the first project of the PSSdb will be the NBSS, along with their uncertainty. And we use the approach by Martin Charto and the Marcus, sorry. And really what we observe is typically it's not a linear decrease actually of each NBSS. Here is the black line represents just a given sample. You actually see a mode here, then a decrease, and then it's kind of reach the same value. And this is actually representative of the limitation of the instrument, where on the smaller end of the size spectrum, we have only a few pixels to depict the organisms. So the uncertainty that is linked to the size is really high, and the probability of imaging an organism that represents only 1 or 2 pixels is actually varying also, so that we can miss organisms. On the other hand, at the higher end of the spectra, we are limited by the volume analyzed, and so as the organisms get rare and rarer, we can only see 1 or 2 organisms in the given volume that was analyzed. So the uncertainty that is linked to the counts themselves are higher. So with this uncertainty, the goal is really to be able to estimate, to do a linear fit of the NBSS, and that is used to provide information on the slope of the size spectrum. And the goal is really to see, for people who have their own instrument or wish to see that at a global scale, is to see pattern in the slope of the organism. So here is illustrated the difference of the slope of UVP profiles, but it's all UVP profiles, so it's hard to see a pattern of the slope, although I would argue that I would kind of see that the slope gets steeper, which could be linked to particle fragmentation with depths. And on the other side, what you see is a breakdown of that same slope, but for day profile versus night profile. And again, we don't see much of a difference, but it's because here I aggregated all the UVP profiles together. So we will, it will be possible, of course, to break that down into specific study area or ecosystem that we're interested in. And then the second and third levels that will be available on PSSdb are the taxa-specific size spectrum. So of course, the idea to use Imager to construct NBSS is because we have a lot of information about the size of the organisms, but also what they are. Now, one of the challenges that came with using taxonomic annotation is the heterogeneity between imaging sensor and also among experts. So here you have represented the diversity of the annotation across all UVP profile at different rank, meaning that here the inner ring is just the distribution of all the image annotated at the phylum level, and then annotated at the class level, order, family, and lastly genus. And the white part are the images that are unassigned to a specific taxonomic rank. So what you see is that typically we are able to annotate all the image to the phylum level, but then as we get thinner into the taxonomic range, then we kind of typically lose some information. So, but some of the taxa are actually very well annotated, like the cyanobacteria for the UVP. So that would be only the trichodesmium colony, which are large enough to be detected by the UVP. And also one of the things you'll notice is the predominance here of the Cercozoa group, which include the Rhizaria. And so, so the goal is then to be able to produce the NBSS and to see shifts in the different taxonomic groups. So that would be also available on PSSdb. And so, like I've mentioned, the Rhizaria, it's something that has been published by Tristan Bière and colleagues in 2016. They've looked at the UVP profile during Tara expedition, and really noticed that the dominance of that group that was previously unknown because they're very fragile, and they used to be disrupted by the method that we're using nets. So it's really something that was new, although I would argue that most of the UVP profiles are located in the subtropics, so that is true for the subtropics, but not so much in the polar regions. Then we observe a shift of the taxonomic composition. But anyway, the first level is then to produce interpolated map. So of the size spectrum, but also of the abundance and the biomass of the different groups. And here you have an example. This is from a recent publication from Leticia Drago, who shows, again, just what I told you, the dominance of the Rhizaria is in the tropics. And this is the surface, this is the epipelagic, and this is the mesopelagic layer. So the goal would be to use the environmental variables such as the climatology, the remote, the satellite, etc., to be able to predict on a global scale the size structure of the different taxon, and at different depths. And with that, I will end, and thank you all for listening.
Great, thank you so much. That is certainly an exciting database that's coming to light. So I'm quite excited to hear about it further. Does anyone have any questions?
Yes, I do have. Thank you, Mathilde, for waking so early. Good morning. I have a question regarding the identification of taxa. I mean, you visibly identify to which organism that particle belongs.
Sorry, can you repeat the question? You were breaking down a little bit.
how do you identify the taxa of a particle?
So, so the goal is really to use the imager, and I've shown you a couple of examples. Let me go back and reshare of what those images look like for the different imager. And so we don't do the annotation ourselves, but we've had people working on their specific project annotate each of those images and say, okay, this is a jellyfish. And sometimes they can just say, okay, here is a jellyfish. Sometimes they can go to the genus and say, oh, this is actually that particular genus. So the goal is then for us, we are not doing any annotation. We're just getting the data as it is. And we are also working on non-annotated and annotated data set just to provide the raw size spectrum. But we certainly wish to include some taxa specific size structure as well.
Thank you. That answers.
Thank you.
Great. Anyone else with a question? Let's see. All right, well, I have one. So I'm just wondering, of course, each of these instruments would have slightly different biases. And I just wonder if someone wanted to combine all of the data sets from these different instruments to answer questions about biomass from a specific region. Is there a way at the moment to account for some of those biases? So like, the nets that give you data that goes into the zoo scan and say a UVP. Yeah, is that something that you're currently working on, or?
Yeah, that's a very good question. So like one thing we've observed with the difference between the UVP and the ZooScan, although they can see the same size, they target the same size, you'll notice that the scale is slightly different. And again, it's what we think is happening is that the ZooScan, with the net, we are disrupting a lot of organisms, so we overestimate it. So right, that's one of the well-known bias for the nets and the ZooScan sampling. So what we are going to provide with the database is matchup point, where we actually have multiple instruments. And so one would be able to, download data only from UVP and only from ZooScan or for both, and then be able to directly compare in terms of abundance, but also specific taxa that are missing, that are, like because of the bias of the method, for instance. So that's something that we're of course ourselves also are interested in looking at the difference between the UVP and the ZooScan. But yeah, I think at this point it's pretty well known that it's just the issue with the net for the ZooScan is can be pretty dramatic. Like it can be a difference of 50% of the total biomass since by the ZooScan. But yeah, that's something that one could look at.
Yeah, cool. That's exciting. All right. Let's see. Anyone else? Let's see. Anyone? No, I think that's it, unless anyone has any more questions. Let's see. Yeah. All right. Well, thank you so much. And thank you so much for waking up so early. A little bit tough this time. We have India, France, and Australia time zones to coordinate. So thank you so much for you both for presenting. It was fascinating talks, and I look forward to following both of your research.
Thanks a lot.
Yeah.
Thank you.
All right. Thanks so much. All right. Bye.